Welcome to Tuesday's session, and I'm very happy to introduce our first speaker, Brändén from KTH. So let me say a few words about Peter. So Peter graduated in 2005 under Inar Stengelsson. Since then, he spent a few years in Michigan, then in Stockholm University. Now he is at KTH. So he won many awards, but I would rather not enumerate them so that I don't steal any more time from Peter. So Peter is going to talk about zeros of multivariate polynomials in combinatorics.
Thank you. Well, thanks for the invitation. You did a very good job of saying my name correctly. The best ever. And I also want to thank you for inviting my two office mates from Italy, Suli Clortide and Brändén. So I will talk about series of multivariate polynomials in combinatorics. So this will be a survey-like talk. I intended to do more survey-like talk, but to minimize the topics. Okay. So the zero restrictions that I will be talking about appear in many different contexts. So here are a few. So in statistical mechanics, for the reason that the Liang program on phase transitions is about just zero restrictions on the partition function of the model. And more, very recently, just last year, a spectacular solution of the Caddy-Sansino problem used these polynomials with these zero restrictions. And then there's the probability theory, also matrix theory, and control theory for obvious reasons. And why does combinatorics always end up in bottom? Can you see that? Can you see the bottom of the? You cannot. You should stand up. Okay, so I will mostly talk about the connections to combinatorics. And the classical connection is unimodality and log concavity. But there's also connections to graph polynomials, of course, and network theory, and also very recently spectral graph theory through the work of Marcus, Spielmann, and Silverstone. Okay, so let us start with something that should be familiar to a lot of people. So these are really rooted polynomials. So we look at a univariate polynomial with, say, with positive coefficients. And the sequence of this the sequence of coefficients of this polynomial is unimodal if it goes up and then goes down. And it's just as, at most one plateau. And a stronger property is log concavity, which we all know, or can easily derive. An even stronger condition is ultra log concavity. And already Newton knew that if the polynomial itself is rerooted, that the sequence is ultra log concave. So this is one reason for combinatorialists to be interested in this, and historically this has been one of the main reasons. It's a very convenient way of proving unimodality for log concavity. Okay. So there are several examples of this.
It's difficult to hear you at the back of the room sometimes.
Then I'll speak up.
Thank you.
So Eulerian polynomials and their generalizations. So these are just the generating polynomials for the descent statistic over the symmetric group. And these are known to be rerooted by I guess, Frobenius was at least the first one that I have found, and the first reference in the literature that I have found to is also often attributed to Harper, but that was later. And another classical instance is matching polynomials. So these are the generating polynomials of matchings in graphs. And this is due to Haleman and Lee. And more generally, independence polynomials of claw-free graphs. These are the generating polynomial of independent sets of vertices. And a graph, well, you cannot see this. There should be an edge here. Someone stole that. So a graph is claw-free that contains no induced claw. And this was proved by Chudnovsky and Seymour in 10 years ago. And there's, of course, orthogonal polynomials that are always rerouted, and characteristic polynomials of permission matrices. So this is a popular list of such polynomials of permission. So what is a multivariate rerouted polynomial? Well, there are several different notions of this, but they are more or less equivalent. But we call a polynomial in n variables with real coefficients. We call it stable or real stable if it's non-vanishing whenever all the variables are in the upper half. Okay, so this is the definition. So this polynomial is going to be stable. Well, why? Because this factor has just non-negative coefficients in front of the variable. So the imaginary part of this factor is going to be positive if all the imaginary parts of the variables are positive. So this factor is stable, and this factor is also stable because the product of two numbers in the upper half plane is never a positive real number. Right? So this is a stable polynomial. And it's a multivariate analog of rerootedness because, well, if we just have one variable with real coefficients, then non-real zeros come in complex conjugate pairs. So if it has non-real zeros, then one better be in the lower half plane. And one in the upper. And of course, if we have a stable polynomial, there are several ways of getting a univariate rerouted polynomial. For example, just by setting all the variables equal. Right? So, as we saw, many important polynomials in combinatorics are rerouted, but can we find some non-trivial multivariate and stable polynomial that projected this? And why would we be interested in that? Well, for several reasons. For one, it provides much stronger inequalities that we will see. Oh, and there was no other reason. Well, there are. So one classical example already known to Haleman, I should say, to Haleman and Lee is the multivariate Haleman and Lee theory, which already appeared in their paper, although the univariate one is the one that's usually used in combinatorial applications until recently. So this is the multivariate generating polynomial for matching. So we have a variable for each vertex, and then we have some non-negative weights, and then we just form the generating polynomial with an appropriate sign. And we sum over all matches. So you can see the red here. I can. So, and of course, in particular, the generating polynomial for matchings is another great source of stable polynomials comes from determinantal polynomials. So given a bunch of Hermitian matrices of the same size, where A1 through AN are supposed to be positive semi-definite, we may form the polynomial which is the determinant of this, the corresponding tensor. And this is going to be stable. And the proof of this is quite simple. By continuity, we may assume that A1 is positive definite. And then we want to prove that P is non-zero whenever the variables are in the upper half plane. So we choose a real vector and a real vector x and a real non-negative or real and positive vector y. So all coordinates are positive. And we want to prove that P is non-zero. Well, what do? Well, we just collect terms, and we get a red Hermitian matrix and a positive semi-definite or positive definite matrix B, because we chose A1 to be positive definite. And we can of course pull out the determinant of B and then conjugate by the square root of B to the negative 1/2, and we see that this is Hermitian, and so of course negative 1 cannot be an eigenvalue of it. So this is non-zero. So this is the simple proof of this big class of stable polynomials. And this is one reason for why they appear all over the place. An amazing fact is that for n equals 2, so just in two variables there is a converse, which follows from the work of Helton and Winnicott, which in turn solved the conjecture by Peter Lax from 1958. So this theorem of Helton and Winnicott says that indeed if we have a real polynomial in two variables of degree inverse d, well, degree exactly d, I should say, then the following are equivalent. That P is stable, and there exists symmetric real d times d matrices A, B, and C, so that A and B are positive semi-definite, and P is given up in this form. And one thing which is amazing is that you can actually choose these to be D by D matrices where D is the degree. And if you try to do this for more variables, you will fail, because you can see that, well, the constraints that your polynomial should be written in this form, it puts a lot of constraints on the number of free parameters. So there's only a triangular number of parameters for A and a triangular number of parameters for B and so forth. And so if you count the number of parameters and you want to try to extend this to say 4 variables, you will fail because you can show that the space of stable polynomials in n variables of degree inverse d has non-empty interior. So it has a maximal number of parameters, and if you count the parameters, you will get a binomial number such as this. And if you try to count the number of free parameters that you get from a pencil of matrices, you will get something much smaller. So this fails for more than 3 variables, and it's an open question how you can try to fix this. So you could, for example, try to fix it with allowing larger matrices, but this turns out to fail. Or you could fix it by trying to sort of raise p to a power, and this fails too. And then you can add an extra factor here, and then we don't know if it fits. And this is the generalized Lax function, but I won't have time to talk about that. So from these determinantal polynomials, we can create a lot of stable polynomials with combinatorial sequences. So given a connected graph, where we choose the vertices to be 1 through n, we may form the multivariate spanning tree polynomial in the variables, well, where we have a variable for each edge, as just the generating polynomial overall spanning trees of T. And then there's the Kirchhoff's matrix tree tip theorem that states that, well, if we form the weighted Laplacian, which is of course a pencil of positive semi-definite matrices, because it's given by A transpose, where A is a positive semi-definite rank 1 matrix. Then the matrix tree theorem says that exactly that. If we delete one column and one row, or the same row from L, then and take the determinant, then we obtain the spanning tree. So this is a large class of combinatorial polynomials that are stable. So spanning tree polynomials are stable. Okay. So why do stable polynomials appear in so many different areas of mathematics, and why are they useful? Well, they of course satisfy strong spectral inequalities because they're defined by matrices. Okay? But if you try to do stuff to your determinantal polynomials, you easily fall out of the class of determinantal polynomials. So for example, if you try to differentiate a determinantal polynomial with respect to one of the variables, then it turns out that you're no longer determinantal anymore, but you are stable. So this is why this is a nice class of polynomials, because you can do a lot of stuff to them and they're still going to be stable. So for example, you can replace one of the variables by a real number. It's not hard to convince yourself of that. Or you could rescale a variable with a non-negative real number. Or you can set a couple of variables to be equal. Or you can, as I said, differentiate by the Gauss-Lucas thing. It's not hard to convince yourself that you can also differentiate with respect to the variables. Okay. But what other closure properties do stable polynomials have? So, in particular, all of these operators are if you view this as operators, they are of course linear, so one can ask which linear operators preserve stability. If you answer this, you have a great toolbox to work with. So to answer this, we have some more terminology. So we look at the space of polynomials of degree at most kappa j in the variable xt. And we look at some linear operator from the space of polynomials with bounded degree into the space of all polynomials. And we form this symbol that carries all the information of your operator. So you just take the image of this specific polynomials where y1 through yn are treated as constants, but they are of course variables. So then you get a 2n variate polynomial, and it turns out that if the rank of t is greater than 2, which most linear operators are, otherwise they are not very interesting, then T preserves real stability if and only if the symbol is real stable. So So preserving real stability in n variables is the same as checking if the symbol is real stable in two n variables. So then, yeah, this enables you to check if you want to deform your polynomial in some way, and you want to see if you're allowed to do that. You just have to check if the corresponding symbol is stable in two n variables. This can, of course, be very hard because there's no efficient algorithm for testing stability. But in particular, as we saw, real-rooted polynomials are stable. So we have a characterization of which linear operators on univariate polynomials preserve real rootedness. And then the symbol looks like this. If you want to look at polynomials of degree at most n. And the special case of the theorem is that, yeah, if you want to check that a linear operator preserves real rootedness, then we just check this if this corresponding symbol is real stable, or equivalently by the Helton-Binikoff theorem, if this symbol is the determinantal polynomial. And this can be checked a little more, it seems. There are
So is there sort of an algorithm to compute the matrices?
yeah, not very efficient. It involves theta functions. Yeah, you can do it. There are softwares for it. So we're still lacking an efficient way of checking. And of course, this Helton-Binikoff theorem is a very deep theorem. It uses hard it's a deep theorem, and we wouldn't expect to then have an easy way to check stability. But there might be. Okay, so let's take an example. So now we have a characterization of which linear operators that preserve real rootedness. So, and a lot of combinatorial polynomials are can be defined by recursions, and recursions are, of course, linear operators. So this gives a way of proving that your generating polynomial is real rooted. So let's take the basic example of Eulerian polynomials, which were the descent generating polynomial of this node. And they satisfy this familiar recursion. We can interpret this as a recursion among the polynomials, such as this. And then we can identify the right-hand side here as a linear operator. And then to prove by induction that the Eulerian polynomials are real-rooted, you just have to check that this particular linear operator preserves real-rootedness. And this can be done easily. So this is, of course, stable because we have positive coefficients here. And this is, of course, stable. And this is. But it's not always that. It's as simple. So now let's say something about inequalities that are satisfied for stable polynomials. And there was an amazing theorem by Grubitz from around 10 years ago that relates to the van Brändén conjecture. It's a vast generalization of the van Brändén conjecture. So we call that a matrix of real numbers is doubly stochastic if it has non-negative entries and if each row and each column sum to 1. And that was this van Brändén conjecture from 1926 that the permanent of a doubly stochastic matrix is bounded below by n factorial n to the n. And equality We have equality if and only if we have a constant matrix with coefficients 1 over n. And this resisted attempts for proof for a long time, and it was then, as often happens, that it's proved simultaneously by two guys. Grigoryev and Falikman proved it in 1979 and 1980. But just recently it was extended dramatically by Gervitz, and the proof was simplified also in the process. So let's explain what we did. So the first simple observation is that the permanent is one of the Taylor coefficients of this polynomial, which is a product of linear forms. You cannot see this here, right?
Put variables to 0.
Pardon?
After differentiation, you want to put variables to 0.
Yeah, but you don't have to, because it has degree n. So it's if you take if you differentiate this, you will get a constant. So yeah, but I could put it this way. But can you see this? Yep. Yeah. So this observation is not hard to do, because we have to choose one from each factor. So we observe that this polynomial here is stable because it's a product of linear forms with positive coefficients. And this being doubly stochastic now translates into a simple property, just that if we take the partial derivative with respect to the variable xi and set all the variables equal to 1, we get 1. Okay. So these two conditions are simply generalized to any polynomial. So we call it a homogeneous polynomial in n variables and of degree n, doubly stochastic if it is stable and satisfies this property. And the amazing theorem of Gervitz says that, well, in this vast generality, the bounded burden conjecture holds. So if we take a doubly stochastic polynomial, this is just a homogeneous polynomial in n variables and of degree n, and which is stable and satisfies this doubly stochastic condition. Then you can bound the coefficient of x1 through xn by this number. And we have again equality if and only if p is a. And this, yeah. And now you can sort of imagine that you have a lot of combinatorial applications of this. You could, for example, look at mixed discriminant, where p is a determinantal polynomial. Then this thing here is the mixed discriminant of your bunch of matrices. Or you could take your favorite polynomial. And the amazing thing is also that similar ideas went into the proof of the Caddison-Singer problem, which was one of the major achievements in mathematics last year. One of the two of these. There was another one about prime numbers. But so they proved this theorem. That maybe takes a while to appreciate. So if you have n positive semi-definite matrices of rank at most 1, such that they sum to the identity matrix, and the traces, or the only non-zero eigenvalue, is less than epsilon for all I, then you can find a partition of your index set, or 1 through n, so that in matrix norm, or operator norm here, the sum over the indices B of the AIs is approximately I over 2. So what does this mean? This means that you can partition this sum into 2 blocks, where both blocks are approximately the same. And they're not only the same, they're equal to I has. So we get approximately the same identity again. And it's sort of unexplored what this means in, well, what you can actually get from this in combinatorial applications. So you can think of the, for example, there are we saw before a bunch of semi-definite matrices of rank at most 1, namely in the definition of the Laplacian, right? So if you have a graph, what does this mean? It means sort of that you can, that for a graph you can partition your graph into 2 pieces, which looks approximately the same, in some sense. Okay, but why does this, well, this is not the Cadison-Singer problem, but more a stronger version of Weaver's conjecture. But Weaver's conjecture implies the Cadison-Singer problem from 1959. And this Cadison-Singer problem is, well, it comes from quantum mechanics, and well, if you don't, I could read it for you, but if you don't want to, but it's it doesn't look anything like this theorem by Marcus Spinman and Srivastava, but this is more of a combinatorial. Well, we were able to formulate it in a very good fashion. Yeah, actually, it works. Okay. So this had vexed the C-star algebra community for a long while until someone used these new methods to prove it. Okay, so what's the pivotal point of the proof by Marcus Spinman and Srivastava? Well, what they need to do is that if you look at it again, homogeneous and stable polynomial of degree D, they associate a univariate polynomial, which is easily seen to be rerouted by the closure properties that we discussed before. And what the proof boils down to is that we want to maximize the maximal zero of this sort of generalized characteristic polynomial under some constraints, and the constraints are sort of linear. They are given by that the partial derivatives evaluated at 1 should be less than or equal to epsilon. And for these slides, we can take epsilon equal to 1 for just convenience. It doesn't really matter. So to get in, they were able to they were not able to maximize the maximal zero, but they were able to get good enough bounds to prove the Cadison-Singer problem. But they have a conjecture about the maximized maximal zero, and it's exactly that the maximal zero of this characteristic polynomial, taken over all p satisfying these constraints, is achieved for the same polynomial that minimizes this in the Fallon-Verdict conjecture. And we get a similar polynomial for general epsilon. So we put epsilon equal to 1. Okay. And if you compute this this characteristic polynomial for this PD, it's not hard to see that what we get is actually a Laguerre polynomial. And zeros of the classical orthogonal polynomials are well studied, so this would give an optimal Weaver's conjecture, then instead of this strange square root of square root of 2 times epsilon plus epsilon squared, we will get a better boundary. Okay. And I can prove that this conjecture is equivalent to the following more innocent conjecture that could probably be attacked with different methods. This conjecture says that the maximal zero, which we're looking for, is realized for a degree d polynomial for which the top coefficient in each variable is non-manageable. So if you can prove this, you can prove the previous conjecture. Okay. So now we switch to completely different. If you don't have any questions. Yeah?
In the Texan Singer, you said that the graphical Poisson matrix gives rise to these rank 1 matrices that sum to the identity.
Well, they don't sum to the identity, but you can relax actually this. They just have to sum to a so you can actually relax this. They don't have to sum to the identity, but then you instead get whatever it sums to. You divide that by half instead. So this is so yeah. So that yeah. So you don't have to sum to it. Okay. Any more questions? Okay, so now, yeah. So when we use this multivariate techniques to prove things about univariate assertions too. So we talked about log concavity before, and we may view log concavity as sort of a nonlinear operator on sequences. So if we have a sequences of real numbers, we may form these expressions that are the definition of log concavity. And then log concavity just says that L applied to your sequence is a non-negative sequence. And it's an I-fold log concave if you apply it I times, it's non-negative. Okay? And it's infinitely log concave if you do it. If it's non-negative for all I. And there was a borrow small conjecture 1, but I thought that I wouldn't have time to explain what that is. So this is the borrow small conjecture 2, that n choose k, from where k goes from 0 to n, is infinitely log concave. This was an innocent looking conjecture. So, but if you try this, if you take L once, you get the Mariana numbers. And the Mariana numbers are known to be log concave. Then actually the generating polynomial is known to be re-rooted. And this was proved for n less than 1450 by McNamara and Sagan. And of course, so this was evidence for the but what several people noted when this conjecture was around was that a stronger statement could hold. So if you have well, of course, if you take the generating polynomial of the binomial coefficients, you get a re-rooted polynomial, namely 1 plus x to the n. And what they observed was that the following seemed to be true: that if you take a polynomial with real and non-positive zeros, then the corresponding polynomial associated to the L operator is also rerouted with non-positive zeros. And this would of course imply the Boros-Moll conjecture because you could keep iterating this and we will get non-negative coefficients here. Yeah. So when I first heard about this, I thought, no, this is not true. This is not a linear operator. So counterintuitive. But then I thought maybe one could prove it using multivariate polynomials, and indeed, if you look at this elementary, well, if you look at this polynomial, symmetric polynomial in n variables of degree 2n, then it turns out that this is stable. And of course, if we have this closure operator, so we can scale this variable setting. So if we look at this polynomial, we can factor this into its linear terms, and then all the factors have, well, and then we can plug in the zeros times t here, and we will get a similar looking polynomial which will be stable again. And from this you can directly prove that this theorem immediately implies the conjecture. And this is often the case that if you look at a univariate statement in a multivariate fashion, you can often find a way to prove it. Yeah, so here is the but this is, well, not the end of the story. So we can also, so we saw that the rows of the Pascal's triangle are infinitely log concave. But we can also look at the columns. And it was conjectured by McNamara and Sagan in 2010, the same paper, that indeed the columns are infinitely log concave. And they have a similar flavor because these columns are polar frequency sequences. And a polar frequency sequence is just a sequence for which all the minors of the corresponding Toeplitz matrices are non-negative. And we may view the corresponding theorem as saying that if we have a P of sequence, a finite P of sequence, and we form this log concavity, and we take this log concavity operator on it, then we get a finite P of sequence again. So this, I guess, correct me if I'm wrong. This led them to conjecture that P of sequences are infinitely log concave. I guess computer experiments. But it's turned out to be false. But if you look at this example. So if this general conjecture is false, well, we have to look at more specifically on what properties do these sequences have. Well, they are interpolated by polynomials, right? So this is a polynomial in M. And so we can ask ourselves if L preserves polynomial polar frequency sequences. Any guess? So you can check that if you take the sequence M squared, this is the Polyar frequency sequence. But if you take the L operator on it, it's not a Polyar frequency sequence. Too bad. But what we have to do, what we realized that the condition that we need is that we should have two consecutive zeros near the origin. So we should, so for example, P of 0 and P of 1 should be 0, or P of 0 and P of negative 1. And then it goes. Then L maps this class of Polyar frequency sequences to the same integer set. So of course, if you look at this has two consecutive zeros. So this solves Salient factor.
So I'm a little bit confused because earlier you used the coefficients of polynomials, but now you look at polynomial sequences.
Yeah. So I look at Polyar. So I have an infinite sequence of numbers, and I want this to be a Polyar frequency sequence. So all the corresponding Toeplitz matrix should be totally positive. But we noted that this is not enough for L to preserve this. So we look for extra conditions, and this extra condition is, well, one extra condition is that it should be interpolated by a polynomial, and it's interpolated by polynomial here. This is why we look at this. And the other extra condition is this boundary condition. Okay. So a natural question is that, is this innocent looking sequence infinitely log concave? Well, this L operator doesn't send it to a totally positive sequence, but it could be infinitely log concave anyhow. And at least for k equals 3 we did computer experiments, and it seems to be, we looked at some small larger k2. So this is an innocent question. Try to look. And another generalization would be to what's special with this log concavity operator. We could take higher determinants. So we could look at something like this. So if we have a polynomial with only real and negative zeros, then does this polynomial also have real and non-negative zeros? Well, the proof technique that I had doesn't work. Because the key to this, the proof that I had, is that we could write this polynomial, multivariate polynomial that we were interested in a clever way, namely as the sort of an almost linear polynomial, but in different variables. So does this identity generalize in some way to higher determinants? I know that Christian does not. Did he? But it could do it in, well, it could generalize. It doesn't generalize in an obvious way, but it could generalize in some way. So now I have 10 minutes left. I could start telling something about a completely different topic again. Namely, stable polynomials and matroid theory. So recall what a matroid is. And we look at the basis exchange axis of defining properties of matroids. And of course, a motivating class of matroids comes from vectors in a vector space. Namely, if we take this set of indices that whose corresponding vectors form a basis of our vector space. And this such matrix are representative of the field of interest. And now the support of a polynomial is just the indices for which the corresponding Taylor coefficient is non-negative. And an amazing theorem by Chowiocki, Sokol, and Wagner connects stable polynomials to macro theory. And it says that the support of a homogeneous multi-affine, meaning it has degree at most 1 in each variable, and stable polynomial is the set of bases of a matrix. So from any stable polynomials, a stable polynomial which is homogeneous and multi-affine, we get a set of bases of a matrix. So one may ask which matroids are representable in this way. And such matroids, they call them weak half-plane property matroids. And an important question here is which matroids are weak half-plane, have this weak half-plane property. And we saw before that the spanning tree polynomial is stable, and of course if you take the support of that, we get the basis of the set of bases of graphic matroids. So the graphic matroids are weak half-plane property matroids. But we also saw that determinantal polynomials were stable. So this can be used easily to prove that if you're representable over the complex numbers, then indeed you're going to be a weak half-plane property matrix. It's just a simple exercise. Okay, so representable matroids are over the complex numbers are weak half-plane property matrices. So one can prove that. Well, on the other side, one can prove that no projective geometry is weak half-plane property, has the weak half-plane property, and a binary matroid has the weak half-plane property, if and only if it's regular. So these are some properties. But now I only have 2 minutes left, so I'll skip some slides. Related to something that June might be. So recall that the characteristic polynomial of a matroid is defined by the Möbius function of the lattice of flats in this way. And there's this conjecture of Rota, Welch, and Hero that's been open for a long while, until very recently, that the coefficients of the characteristic polynomial form a log concave sequence. And it's easy to see that if we put q equals 1, we get 0 here, because we have a Möbius function up here, so we can divide by q minus 1. And an amazing theorem by Junhue and Katz says that if you're representable over any field, over some field, then the coefficients of this truncated or augmented characteristic polynomial form a log concave sequence. And it's easy to see from this that this polynomial too form a log concave sequence. But their proof doesn't, well, it's only speculations on how to prove it in a non-representable case. But maybe one can prove it for the weak half-plane property matrix, because then you still have some algebraic properties. And this, one can see that sort of the combinatorics of representable macros, where you have the subspace arrangements, then instead of subspace arrangements, you will, in the weak apparent property macro case, you will have arrangements of faces of certain hyperbolicity cones. So it could be that June's proof is actually can be extended to this case. I think I'll end here.
We have time for two quick questions.
So back to the infinite log concave stuff. So n plus k, choose k, the ordinary generating function for that is 1 over a power of 1 minus t. And for n to the k, you're open to question about infinite log concavity, the Eulerian polynomial over a power.
Yeah.
Right, so, I mean, is there some kind of analysis of the ordinary generating function that helps with this infinite log concavity? Or infinity? I mean,
So we needed this, well, for the proof to go through, we need polynomial polyfrequency sequences, and these are the form that you described. So we need this form for the proof to go through. But we also need some extra properties, and these are these boundary conditions. So we need two consecutive zeros, and n to the 3 just as 1 consecutive zero. It's not enough.
One more question?
Yeah?
Okay. Are there families of matrices that satisfy the weak apparent property but are not representable?
Yeah.
You said that already.
But no, I didn't. I skipped that slide. The Banos macro is the first, and this is. Yeah. So the Banos cube is not representable over any field, but it has the weak apparent property as was shown by Wagner and Ray by sort of represented certain polynomials by non-negative polynomials by sums of right. They proved that certain polynomials were non-negative by representing them as sums of squares, and from this you could deduce that we can. But sort of, there's not many known. Although some people have extended this. And this is actually very useful in this generalized lapse